Hi, my name is Rohit, and today I'm going to talk about a microarchitectural side channel attack, which is referred to as the Spectre attack. Presented at the 2019 IEEE Symposium on Security and Privacy, it's authored by multiple individuals from both academia and industry. It's actually referred to as one of the breakthrough papers in hardware security. So, discussing about physical side channel attacks. So the paper states that physical side channel attacks can be done by exploiting software or exploiting hardware. So if we look at software, then we have attacks like buffer overflows or double free errors. And pertaining to hardware, we have attacks like cache timing attacks and the attacks which basically involve training the branch prediction table or which exploit the branch prediction history or the branch target buffer of the target system. So these are like the two ways in which physical side channel attacks can be implemented. And so in this paper, we are going to be discussing about an attack that uses the property of speculative execution of modern computer architectures. So a brief background into the concepts that we'll be requiring for understanding this paper. The first is what we call an out-of-order execution. So we know that we have two ways in which programs can run. One's a sequential one, and the other, what we call, is an out-of-order execution. So the basic reason why we look into out-of-order execution is because naturally we need speed. And if we have the resources, then really there is no logic in waiting for something when something else doesn't depend on it. What I mean by it is, let's take a look at the series of instructions. So the instructions that are marked in the red boxes, those are the ones that are actually independent of each other. So if you look at I1, I2, I5, I6, I7, so all of these instructions that are marked in the red boxes, they can be executed simultaneously. Let's say we assume that we have unlimited hardware resources, then all of these instructions can be executed at the same time. So rather than going sequentially in one cycle, instead of completing one instruction, now you're like completing 8 instructions in one cycle. Obviously, in a modern system, we don't have like unlimited resources like ALUs or load and store units. But what I mean is out-of-order execution really speeds up the system, and that is the reason why we are choosing it over sequential execution. So this diagram is like a brief overview on if all of these instructions marked in the red boxes are executed simultaneously, then in the first layer, we get these independent instructions, then the instructions that depend on those, and then the other codependent instructions. So I'd say the main advantage of out-of-order processor is that it avoids the instruction wait time, even when we have the hardware resources. And so basically, we can say that out-of-order processors or the out-of-order instructions are executed by the availability of their operands. So an out-of-order execution paradigm increases the utilization of the processor's components by allowing further instructions which are going to be executed down the stream immediately, or execute those which are supposed to be executed down the stream at this very instance. So we're actually saving time on executing future instructions. So this is the entire logic behind out-of-order execution. Another important concept is speculative execution, and I'd say it's the most important concept while understanding this paper. Speculative execution, it's quite simple to understand. The literal meaning is while the CPU or while the processor is doing a particular instruction, it speculates what the next instruction is going to be. So it's an optimization technique in which a CPU performs a series of tasks before it is prompted to. So let's assume that we have a RISC-V architecture. So we know that it's a 5-stage pipeline with fetch, decode, execute, memory, and write back. So let's say that this is our assembly code. It's basically a simple loop. And on the left-hand side in this box table, we have the exact time cycle at which a particular instruction is in which stage of the pipeline. So let's say we start with the ADDI, and let's say it executes from T1 to T5. So in T2, when ADDI is in the decode stage, the next instruction, which is the branch equal, is fetched. When branch equal is in the decode stage, the next instruction, which is the SLLI, is fetched. So basically, we are fetching the next instruction immediately after the previous instruction decodes. Now, by speculative execution, I mean, let's say we have a branched instruction. So in the first try, we have EDDI, which is x2. We have x0 and 2. So the first instruction is basically going to add 2 to x0 and store it in x2. So now the BEQ statement will see if x2 and x0 are equal. If they are equal, then the branch should jump to this index, which is 0x2014. If it's not, then it goes to the next consecutive instruction. So there's exactly what we are doing in here. So in the first iteration, I'm executing ADDI, BEQ, SLLI, ADDI, and JL. And JL is a simple jump instruction, which just says that jump back to this position, which is 2004 branch equals. Now, and after the first JAL, you can see that the store instruction and the ADDI instruction are also fetched. And this is what we mean by speculative execution. So the JAL instruction is fetched. When the JL is decoded, I'm going to fetch an instruction that comes after JL, which is store. When store is fetched, I'm going to fetch something that comes after store, which is the ADDI. And basically, in the execute stage, the JAL gets to know that, oh, it has to jump to a previous location. So these two instructions, which are already in the pipeline, the store and the ADDI, they are squashed. And by squashed, we mean that these instructions do not exactly complete. And this is what we call transient instructions. And the entire concept of a Spectre attack surrounds these transient instructions. So this is just a basic example, but in the Spectre attack, there can be a series of instructions that come after a jump instruction or a branch equal instruction. In modern processors, we have very deep pipelines. So until the execute stage, you can have hundreds of instructions that are rapidly speculatively executed. Many of these instructions can really make some hardware changes. And even though they are squashed, these hardware changes cannot return to their original state. And that's exactly what the Spectre attack exploits. The next important concept is branch prediction. So the most common algorithm for it is the 2-bit saturating counter. So let's say we again take a look at this program and the box table. So it's something similar to what we did in the previous question. In the previous slide, I'm sorry. So we have the load instruction, and then we have the branch equal instruction. And you can see that the instructions that are marked in yellow, those are the ones that are speculatively fetched, because these instructions are already in the pipeline, and these are what we call as transient instructions. So they are going to be squashed, and we're basically going to go to SLLI. So if you see on these blue highlighted ones, that is where the branch predictor exactly works. So there's an initial state in the branch history table, and the branch predictor acts as per the branch history table. So we have the weakly taken one, the strongly taken one, the weakly not taken one, and the strongly not taken one. The processor initiates from either one of these stages, and then let's say we start from the weakly not taken one. So every time the branch is taken, my counter is gonna increment to a weakly taken one. So the next time when I hit the same branch, it needs to be taken, because now it's in a weakly taken stage. And that's basically how branch prediction works. And so in the Spectre attack, branch prediction is combined with speculative execution to exploit these transient instructions and fetch location from places that are not supposed to be accessed. Like, in this case, I think we're assuming that it's a weakly not taken one. So initially it's not taken. So it takes, it's weakly not taken. So when we hit the BEQ, all of the transient instructions are squashed. The next time the processor realizes that it took an incorrect branch, so it reverts back to its, how can I say, a checkpoint, and it starts execution from SLLI. So SLLI executes, ADDI executes, JAL executes. Now JAL just tells you to go back to 2004 memory location. And this time, my branch was on weakly not taken, but it was taken. So now it increments to the weakly taken stage. So this time, if you see at the cursor, we are not going to fetch any transient instructions, because this time it correctly speculates that the branch is going to be true. So this is basically training the branch predictor to understand that, yes, the branch is going to be true. And that's exactly what the Spectre attack exploits. So speculative execution and branch prediction, quite some important terms when it comes to explaining the Spectre attack. The next is memory hierarchy, quite easy to understand. So the cache is divided into fixed size chunks, which are typically we call cache lines. So we have registers, caches, main memories, flash disks. So our area of interest surrounds caches and main memory. So we have the L1 cache, we have the L2 cache, and then we have the last level cache, which is common to all the cores. So by microarchitectural side channel, even a cache can serve as a microarchitectural side channel to leak data. And in Spectre attack, in one of the variants of Spectre attack, we store data in the cache and then retrieve it in another function. So we are using cache as a medium for accessing data and then storing data, which was not supposed to be accessed in the first place. And then side channels are like hardware components, not exactly caches. They can be caches, they can be timers, they can be registers, they can be anything to which data can be stored and later accessed. So these are hardware side channels. So in this paper, we use the flush plus reload technique and its variant, the evict plus reload technique, for leaking sensitive information. Another important aspect is return-oriented programming. This comes into picture for the second variant of the Spectre attack. But return-oriented programming is basically a technique that allows an attacker to hijack the control flow and make a victim perform complex operations by chaining together machine code snippets called gadgets. And this is exactly what we're going to discuss in the second variant of the Spectre attack, which involves programming a gadget and then accessing malicious memory locations every time the gadget runs. So as the last statement says, when executed, each return instruction jumps to a destination address from the stack. And because the attacker controls this series of addresses, each return effectively jumps to a next malicious location. So a brief overview into the attack. So the Spectre attack induces a victim to speculatively perform operations that would not occur during a strictly serialized in-order processing of the program, but which leak the victim's confidential information via a covert channel to the adversary. So the entire background of a Spectre attack is leaking information into a side channel, but the system thinks that no, it's working correctly. All the while, some hardware has been changed in the system, and we just take information from that hardware. So it's basically a game of hide and seek. So discussing the first variant, which states exploiting the conditional branch misprediction. So in this case, we focus on the branch predictor. So we are basically making the branch predictor predict a particular outcome and then forcing the branch to speculatively bring in instructions into the pipeline, which are actually not supposed to come in the pipeline. So let's say considering a case where the code in list 1 is a part of a function. So we have if x is less than array 1 size, and inside we have y is equal to array 2, array 1x into 4096. So what we are going to do is this value of x, we are going to train this branch to always assume that this if condition holds true. And I run the program once, the if condition is true, great. Now the branch thinks that the next time my if condition again might be true. Again, I run it the second time, my if condition is true. This time the machine now trusts the execution that, every time I run, the if is going to be true. So let's say at a later on iteration, when my if statement is actually executed or is actually supposed to be false, and it is going to be false, but by the time the processor realizes that it is false, it's already speculatively executed a host of instructions and already done a lot of changes in the physical parameters. So we, as it says here, we are training the branch predictor to mispredict the outcome of the if loop. So we can say that if the if is true, and the prediction is true, then we get really fast execution. But if the if is speculated to be true and it turns out to be false, then the execution really slows down, because now the value of X is not in the cache, it's probably in the main memory. So it takes a lot of cycles to fetch a particular instruction from main memory. And in all this time wherein the processor fetches something from the main memory, a lot of speculative instructions are getting executed. So we'll discuss the exact program of this just in a few minutes. So the experimental result states that the Spectre vulnerability was observed across a host of different CPUs: the Intel Ivy Bridge, Intel Haswell, Broadwell, Skylake, Kaby Lake. It affected both Intel and AMD. So an example that's stated in the paper states that on Haswell i7, the victim code in variant 1 works with up to 188 simple instructions inserted in the source code between the if statement and the line accessing array 1, array 2, which is just below the 192 micro-ops that fit in the reorder buffer of this processor. So basically what this means is that in one of the previous slides, we just had a 5-stage pipeline, which was RISC-V. So we have a reorder buffer, which is a hardware that stores instructions. These instructions are executed, but they are not committed. So the size of the reorder buffer varies in the modern processors. So in very simplistic terms, by the time the if condition exactly comes to know if it is true or if it is false, 188 instructions have already executed inside the loop. And I mean, even though it's very fast, 188 instructions is a huge number of instructions to access some data that was not supposed to be accessed. So let's take a look at the implementation in C. So it's a relatively bigger code, but let's just focus on the victim function. The victim function, as we discussed in one of the previous slides. So we have the if X is less than the array1 size, temp and is array2, array1X into 5 and 2. So the array1X in this case is what accesses the, how I can say, the forbidden memory location. It transfers the data into array2, and later on we retrieve this data from array2 using the CLFlush instruction, as you can see in this case. The second variant of the Spectre attack discusses about poisoning indirect branches. So in this, the adversary trains the branch predictor with malicious destinations such that speculative execution continues at a location chosen by adversary. So in the first variant, we were sending the data to the cache location or sending a data to a side channel. In this variant of the attack, we are redirecting it to a malicious memory location where the Spectre gadget would be executed. So in short, we just jump from one malicious address to another. So what I mean by that is, let's say I jump to my first Spectre gadget. At the end of the Spectre gadget, the how can I say, the code will again redirect it to another memory location that is another malicious memory location. So it's basically a chain of malicious code that runs. So again, looking at the experimental results, the branch poisoning variant was observed in Intel Ivy Bridge, Haswell, Broadwell, Skylake, and AMD Ryzen. Pretty much all of the CPUs which showed vulnerability to variant 1 also showed vulnerability to variant 2. An example being the Haswell processor, wherein the victim process executed 2.7 million iterations per second, and the attack successfully poisoned the final jump 99% of the time. A similar statistic for the Intel Kaby Lake. Now, going to a simple proof of concept. So the speculative execution of this gadget with attacker control EBX and EDI allows an adversary to read the memories, the victim's memory. So it's basically, as I reiterated before, it's a Spectre gadget that executes as a result of a memory location which the branch predictor was trained to go to. This executes the code in the Spectre gadget, and this Spectre gadget redirects it again to a different malicious memory location. So it's basically a chain of malicious memory locations wherein a chain of gadgets are performed. So the attacker can then leak memory by choosing the values for EBX and EDI. So there are other variations of this as well. The first being evict plus time, wherein if we have the just a second. So wherein we have the evict plus time attack, which works by measuring the timing of operations that depends on the state of the cache. So let's say in this case, suppose the register R1 contains a secret value. And if the speculatively executed memory read of array R1 is a cache hit, then nothing will go on the memory bus and the read from R2 will initiate quickly. So basically it says that if R1 is in the cache, then it's going to be executed pretty quickly. And then the next instruction R2 is going to be executed. But if the R1 is not in the cache, then that means that we need to take it from the main memory into the cache, and this requires a longer amount of time. And this results in a different timing for the victim thread. In addition, we have another component, which is the instruction timing one. A similar logic to the evict plus time, but in this case, let's say the first instruction, that is multiply R1, R2, takes a much longer time. So in this case, the next instruction, multiply R3, R4, will either be an out of order execution or the misprediction would be recognized. So in this case, the timing of the first instruction affects the flow of the second instruction. And the last variant, that is the contention on register file, it's something similar to the above two. I mean, if the condition on R1 in the second if is true, then an extra speculative checkpoint will be created. Then if condition on R1 is false. So basically it's a nested if, and so every time I execute any branch statement, the system saves a checkpoint to which the system reverts back if it's a mispredict. In this case, it just creates multiple checkpoints because we have nested if loops. So these multiple checkpoints sort of reduces the speed of the program. So we have a range of different mitigation options that have been discussed in this paper. But quite honestly, none of the mitigation options provide, a sure shot solution to the Spectre attack. So the first being preventing speculative execution. So this again brings us to the question that do we choose the speed of the system or the safety of the system? So do we just shut down speculative execution because it's vulnerable to Spectre attacks, or we just continue with speculative execution and see at other mitigation options? So, preventing speculative execution, even though seems like a direct and effective countermeasure, but it would cause significant degradation in the performance of the processor. The next being preventing access to secret data. So there's although current processors do not appear to have methods that allow software to disable speculative execution, such models could be added in future processors. But as I said, one such measure used by the Google Chrome web browser is to execute each website in a separate process. Now, this can provide you protection against the second variant of the attack, but its efficiency or its mitigation limit against the first variant is still not quite discussed. Then we have preventing data from entering covert channels. Future processors could potentially track whether the data was fetched as a result of a speculative operation or not, and this can prevent the data from being used in subsequent operations. But today there doesn't seem to be any capability that can actually tag data to see if it's come from a speculatively executed instruction or a not a sequentially or a non-speculative instruction. Then we have limiting the data extraction from covert channels. Again, this is something that's not been entirely, realized in today's architectures. But let's say we do get an option of limiting the data that can be extracted from the covert channels, and that can provide an effective countermeasure against the Spectre attack. But this just decreases the attack performance. It does not guarantee that the attack would absolutely be impossible to be done. This just increases the attacker's overhead. So we can say that if we limit the data extraction to an extent that the amount of time that the attacker takes to extract the information is probably more than the importance of the information itself, then in this case, we can say that this particular solution can be a good mitigation option. And the last mitigation option is preventing branch poisoning. Now, to prevent indirect branch poisoning, Intel and AMD extended the ISA with a mechanism for controlling indirect branches. Now, this mechanism consisted of three controls, which were specifically indirect branch restricted speculation, single thread indirect branch prediction. But it's not exactly in this, I can say, in the scope of this paper. Because I mean, one can read about it if we go to the document of the Intel's microprocessor. And another solution which Google suggested was using red pull lines. So a red pull line is a code sequence that replaces indirect branches with return instructions. So the construct further contains code that makes sure that the return instruction is predicted to an endless loop rather than through a return stack buffer. So basically, this again just adds to the attacker's overhead using RUT instructions. So in the conclusion, I can say that this issue again comes to the vital question on do we need speed or do we need security? So a fundamental assumption in software security is that the processor will faithfully execute program instructions, including its safety checks. But Spectre is, I mean, it's a vulnerability which actually uses one of the most important property of the processor, which is speculative execution. And so there's not much that can be done other than, just reducing speculative execution or just going away from speculative execution. But then again, we have a big trade-off between security and performance. So the vulnerabilities in this paper arise from a long-standing focus in the technology industry on maximizing performance. But again, we ask the question, at what cost? So this is all that I had to discuss about the Spectre attack. It's quite an interesting attack, and you can definitely check the paper out. It's available on Google and it's free. So it's a 13-page paper with code that's given in the last few pages. Having done computer architecture in the previous semester, for me, it was relatively easy to understand this paper. But yeah, I mean, in this presentation, I've given a thorough background. So I think you should try to check this paper once. So thank you. That would be all that I had to discuss on Spectre attacks.